Today we're going to take a look at what's called the Fundamental Theorem of Calculus. There's two parts to the Fundamental Theorem of Calculus. So the first part here, and we're just going to state the theorems to begin. And then we're going to go ahead and prove them afterwards. So the first part of the Fundamental Theorem of Calculus says that if we have a function f that's continuous on the closed interval, we're going to note that it's important that it's a closed interval from a to b, and we have some other function, capital F of x, which we've defined as capital F is equal to an integral from a to x, right, where a is some constant, of f of t dt little f of t, then capital F of x is differentiable on that interval, and that the derivative of capital F, which is the derivative of the integral from a constant, to x of f of t dt, is just equal to f of x. So what's this saying? Well, effectively, all this is really telling us is that if we've got a function that capital F is supposed to be a function that represents the integral of another function, little f, then the derivative of capital F is equal to little f. It's saying that derivatives and integrals are effectively inverse operations of each other. I have a function, I take its integral. When I take that derivative again, I should come back to the original function. That's part one. Part two says that if capital F of x is an antiderivative, and antiderivative is just another way of talking about an integral, right? If it's some antiderivative of little f of x on the closed interval a to b, then the integral from a to b of little f of x is equal to that other function, capital F, evaluated at b, minus capital F, evaluated at a. So these are the two parts of the Fundamental Theorem of Calculus. And we're gonna prove them both here in just a second. But before we do that, we're gonna look at a couple of other rules that apply for functions in their integrals, continuous functions in their integrals. One is similar to a rule we've seen before. If you've got a function with a constant inside the integral, you can move that constant out in front of the integral. Second one, again, is the one we've seen with limits and derivatives. The integral from a to b of two functions being added together can be separated out into two different integrals on that same interval, a to b. Or likewise, we could take two separate integrals and put them together. So it, of course, works in both directions. The third one, which is exceptionally important, they're all important, but this one we're going to for sure use in just a little bit, is that the integral from a to a of f of x, so any function, is equal to 0. And hopefully this kind of makes some intuitive sense. When we talk about an integral of a function, we're talking about the area under the curve. Well, if I have some function, here's f of x, and I say, here's a, what's the area under that curve from a to a? Well, there's no interval that I'm looking at. There's no width to that piece that I'm talking about, so therefore there can't be any area under that curve. The fourth one, the integral from a to b of f of x is equal to the opposite of the integral from b to a. So effectively, that means when we're moving from left to right, a to b, the values of an integral would be a positive value if we're above the x-axis. But if we were to try and do it the other direction, from right to left, we end up with a negative value. And then lastly, the integral from a to b plus the integral from b to c should be equal to the integral from a to c. So if we take a look at that, here's some function f of x, and here's a and b and c. Well, if I have the integral from a to b, this right here, and if I have the integral from b to c, this right here, well, if I add those together, I ought to get the integral from a to c of f of x dx. And likewise, we could take the whole thing from a to c and subtract one of these two pieces to get the other piece. So we're going to utilize these, all these different rules in this, well, not all these rules, but a couple of these rules today as we do the proofs. And then we'll use all of these rules towards the end when we look at some problems that are common on the AP test using the Fundamental Theorem of Calculus and using just basic integral rules to evaluate things. So with the whole thing that we're going to be really focusing on today is proving this fundamental theorem of calculus. And so I've started us off here with a picture of some function f of x, and we've got some chunk of that function that we've got an array under it that I've highlighted here in red. We're calling that capital F of x. Capital F of x represents a function that is the area underneath f of x on any interval beginning at a. So it could be going from a to x, or it could be going from a to x plus h, or it could be going to a to b over here, or we could even have it going, somewhere within a to x. We call that c. Right? So capital F is just a function that if I evaluate it at some x value, tells me the area underneath little f of x, starting at a to whatever that x value I chose it. And so we're going to use this to help us prove part one of the fundamental theorem of calculus. So you can see I've got from a to x highlighted in red, and then I've got a blue section, which I've got highlighted as the area from x to x plus h. And we're going to call that delta f, or a change in the value of the function. And in this case, it happens to be the change in the value of capital F as we go from x to x plus h. So we could say that the value of capital F should be equal to, there's a couple different things we could say. One is that value is equal to an integral from x to x plus h of little f of t dt. And we use t as a dummy variable here. You kind of just have to get used to that. We use the t's and the x's interchangeably because we can't define them as the same thing within different pieces of our proof. So the integral, or the area underneath f from x to x plus h, should be the value of delta f. Now we could also say that this value should be equal to capital F of x plus h minus capital F of x. And hopefully that makes a little bit of sense there, because really what we're talking about is, well, capital F of x plus h is the area from a to x plus h, and capital F of x is the area from a to x, as we defined it earlier. So if I were to take that bigger one, the blue and the red, and subtract off just the red piece, I'd be left with the blue piece. And that's exactly what this is saying right here. And so that's using one of those integral rules, that last integral rule that we talked about down here. So we've got a value, we've got something that we know that capital F, the delta capital F represents, but we don't have an exact, a real exact value for it. And if we don't know how to find the integral of little f right here, and if we didn't actually know what the function capital of f of x was, if all we knew was it was called capital F of x, we would need to approximate that area, right? And we've used lots of different ways to approximate areas. And one way, of course, was using rectangles. And so if we think about that, we could approximate this using a rectangle. And we could say that this area is approximately equal to whatever this width is. Well, that width is x plus h minus x. So that width is just h. And then we have to multiply it by some value up here. Well, it doesn't really matter which value we use. They're all pretty similar anyway. To give us that rectangle, we'll just stick with this first value right here. Now, we could use any arbitrary value here. We can still make this work. But picking the first value at x is going to make this just a little bit easier for us. So we've got delta capital F should be approximately equal to h times little f of x. So now we kind of got to go back and think about what is it that we were trying to figure out. Well, the first part of the fundamental theorem of calculus says that the derivative of our function capital F should equal little f. Right? And so if we're thinking about what is the derivative of capital F, well, in terms of a derivative of a function, we know that the derivative with respect to x of capital F of x, which we know as f prime of x, right, should be written as a limit as h approaches 0 of capital F of x plus h minus capital F of x all over h. And of course, what we really do want to do is we want to make h approach 0 here, because that's what we're trying to figure out, is how much this area is changing at an instantaneous, what its instantaneous rate of change of that area is on a very tiny little interval. And so what we're looking at here then is effectively the derivative of capital F is equal to this limit, but this value in the numerator, capital F of x plus h minus capital F of x, is approximately equal on small scales, on a very small, infinitely small scale, equal to h times little f of x. And so all I'm going to do is I'm going to replace that numerator with my approximation for capital F, and say this then becomes a limit as h approaches 0 of h f of x over h. Well, obviously the h's cancel, and we have the limit as h approaches 0 of f of x, which just is f of x. And so that's telling us that given this situation where we're talking about one function that represents the area under the curve of another function, so capital F representing the area under the curve little f, the derivative of capital F, or f prime of x, is equal to little f of x. And that's exactly what our fundamental theorem of calculus is saying, that capital F prime, or the derivative of the integral from a to x of f, is equal to f of x. So we've proved part one of the fundamental theorem of calculus. Now, that's a nice little geometric proof that's kind of like algebraically a little bit grounded in algebra as well. There's a much more formal proof of this that I think we'll go through right now as well. Keeping in mind from the start that we know that capital F of x is equal to the integral from a to x of f of t dt. That was what we first started with way back at the beginning with our first part of the fundamental theorem of calculus. And so, as we said a minute ago, right, this is telling us that f prime of x, or a derivative of that, is equal to the limit as h approaches 0 of capital F of x plus h minus capital F of x all over h. And so instead of writing it as over h, I'm actually going to sort of rewrite this as the limit as h approaches 0 of 1 over h times just the capital F of x plus h minus capital F of x piece of it. And from there, I think since we know what capital F of x is, capital F of x is this function here with the integral in it, we could replace, well, first off, we could replace the capital F of x here with that, and I could replace the capital F of x plus h right here with this same thing, except I'd have to replace the x with an x plus h. So that'd tell us that this is now equal to a limit as h approaches 0 of 1 over h times, and then we'll have an integral from a to x plus h of f of t dt minus an integral from a to x of f of t dt as well. So it's kind of a messy looking integral now. But the nice thing about that is, if we again think back to those integral rules, to what we were just kind of looking at before, if I have an integral from a to x plus h and an integral from a to x, and I'm subtracting the one from a to x from the one from a to x plus h, okay? So we're looking at here, a to x plus h minus a to x, just like we did before, is just the integral from x to x plus h of f of t dt. So I can now say this is equal to the limit as h approaches 0 of 1 over h times an integral from x to x plus h of f of t dt. So it's getting a little bit simpler. Now, at this point, we're going to take just a second here and think about the fact that we're talking about a function that we know is continuous on a closed interval from originally from a to b, where x and x plus h are within that interval from a to b. Well, if you have a function that's continuous on a closed interval from a to b, with, like I said, x and x plus h in that interval, that means that f must be continuous on the interval from x to x plus h, on that closed interval from x to x plus h. Right? So we know that f of x, I'm going to write this out, we have f of x is continuous on x to x plus h. Well, we only have one theorem that's really told us a lot about something that's true about functions when they're continuous on closed intervals, and that's the mean, or not the mean value, the extreme value theorem. So we could say by the extreme value theorem, that means that f of x has a min and a max on that closed interval x to x plus h. And that is 100% guaranteed, right? If you have a function continuous on a closed interval, it's guaranteed to have that. I should clarify those are absolute min and max on that interval. So what I'm going to do is I'm going to now say that on the closed interval from x to x plus h, the absolute min of f of x, I'm going to call it, we'll just call it lowercase m. And the absolute max of f, we'll just call it capital M. And we know that those two things must exist, which is telling us that we know that m is less than or equal to the function, which is less than or equal to its maximum. And this is guaranteed to be true for some value on the closed interval. Or, I would say some value. Just true on. Let me say that. We should say it's true on x plus h. Well, and since f is a continuous function, that means that we are able to, continuous functions are integrable, means you can take the integral. That means that the integral from x to x plus h, whatever that minimum value is, must also be less than or equal to the integral from x to x plus h of f of t dt, which must be less than or equal to the integral from x to x plus h of that maximum value times dt. And if we think about what the integral of the minimum value is, well, a function that represents a minimum value is just representing a constant. And if we are going to take an integral of a constant, right, that's just going to give us a rectangle. It's going to be a rectangle that has a width equal to whatever the difference between x and x plus h are, and a height equal to m. Well, what's the difference between x plus h and x? It's just h. So that tells us that the value or the area underneath a function represented by little m from x to x plus h ought to just be little m times h. And this middle here is still the same thing, because we don't really know what that is offhand right now. And then on the outside here, we've also got a capital M as our height of this, this rectangle that we're making the area of, with a width of h. And so we've got a nice little inequality here. And it's telling us that little m is less than or equal to the integral from x to x plus h of f of t dt is less than or equal to capital M times h. Well, hopefully what we then notice here is that this right here is almost the same as what we had right here. Right? We're just missing the 1 over h that we had multiplied out in front of it. Well, I think it's perfectly acceptable for me to divide every piece of this by h. Now, of course, if we were really doing this formally, we'd do from the left and from the right here, because h could be a positive number, or h could be a negative value. And as we in a minute, we're going to have a limit as h approaches 0. We could be approaching 0 from the right or from the left-hand side. And so we do two cases, one where h is positive and one where h is negative, and we have to flip some inequality signs, but it all works out the same. So we're just going to kind of do it the one way here. We're just going to do it assuming that h is a positive value. And we're going to assume that when we approach, when h approaches 0, we're going to do it from the right-hand side. We're just going to divide all these by h. So the first one's just going to give us m, and that's now going to be less than or equal to that thing that we had before, 1 over h times the integral from x to x plus h of f of t dt is less than or equal to capital M times h divided by h is just m, capital M. So now, as I take a limit as h approaches 0 of little m, we have to kind of conceptually think about this. Well, what was little m? Little m was a minimum value of f of x on the interval from x to x plus h. Well, as h becomes 0, as that interval becomes 0, there's only one singular value that f of x could take on. Okay? The only value it can take on is whatever that value is. It's just f of x. And the same ends up being true over here for the maximum, right? If their interval is infinitely small, that maximum value is also the value of the function. And so what that tells us is that by the squeeze theorem, it's been a while since we've used the squeeze theorem, but we've got one continuous function whose limit is f of x, and another continuous function whose limit is f of x. And we've got another function in the middle that's squeezed between them that tells us that the limit as h approaches 0 of 1 over h times the integral from x to x plus h of f of t dt is equal to f of x as well. And, well, way back at the start, we said that this limit right here was equal to f prime of x. And so that's telling us that the derivative of capital F prime is equal to little f, under the assumption that we were working with that capital F was the integral from a to x of f of t. So that's proving to us, once again, in just a second way for that proof, that the derivative of an integral is just the original function. So what that leaves us with now is the second part of fundamental theorem of calculus. So if we actually, we'll go back up real quick. The second part of it right here is just saying that if we have some antiderivative, some integral of little f of x, which is capital F of x, then the integral from a to b of little f is capital F of b minus capital F of a. So by that same logic, then, we should be allowed to define some other function, capital G of x, also as the integral from a to x f of t dt, right? So that g prime is also equal to f. Doesn't matter what letter I use, right? Capital G, capital F, capital Q, it doesn't really matter. Part 1 of the fundamental theorem of calculus says that I can do that. But I want f and g to be two different functions. I want two completely distinct functions that have the same derivative. So we have to think about what's going to be true for that to be the case. Well, in order for that to be true, for two functions to have the same derivative, but to be different from each other, they have to differ by a constant. Right? If I had the function 2x and the function 2x plus 5, they have the same derivative. But 2x and 2x plus 5 differ by a constant. Right? X squared and x squared minus 1 have the same derivative, but they differ by a constant. So for f and g to be two distinct functions, they have to have a differ by a constant, which would mean that f of b minus f of a should equal g of b plus some constant minus g of a plus some constant. So that we could then see, hopefully, as I simplify that, g of b plus c minus g of a plus c, that negative sign distributes through, and the constants cancel out. So f of b minus f of a ought to be equal to g of b minus g of a. Now, that doesn't really solve anything for us here, but it's a piece of what we're going to need to use. So we've set up here that we know that g of x is equal to the integral from a to x of f of t dt. Well, what does that tell us about the value of g of a? Well, g of a then must be an integral from a to a of f of t dt. From our rules before, the integral from a to a of any function is just equal to 0. So g of a must be equal to 0. And since we know that g at some value minus f at some value must equal some constant, we're going to get used to seeing c as a constant, that must tell us that since g of a is equal to 0, that tells us that that constant that they differ by is negative f of a. And kind of following along with that, that's going to tell us then that if g of a is 0, that should tell us that since f of b minus f of a was equal to g of b minus g of a, that should then tell us that just capital F of b minus capital F of a is equal to g of b. Once again, showing us that g and f, g of b minus f of b, if I track that over, g of b minus f of b is equal to negative f of a, showing that at a and at b, they differ by the same constant. That constant is negative capital F of a. Well, so then we kind of need to go back and think, well, what is capital G of b? Well, capital G of b, we go back to our original assumption here. Capital G of x was the integral from a to x of little f of t. So capital G of b ought to be an integral from a to b of f of t dt. the value for g of b was just f of b, capital F of b, minus capital F of a. And this right here is exactly what we were trying to prove. That's what the fundamental theorem of calculus there, way back here, said that if capital F is some antiderivative of little f, then the antiderivative from a to b of little f is capital F of b capital F of a. And we've now proven it by taking two different functions, right, capital F and capital G, that are both antiderivatives of little f. So that's the end of what we're going to be doing with our proofs here. We're going to go into a couple of little problems that are relatively common on the AP test. So one of those is they'll ask you to take the derivative of an integral from a constant to x of some function. And this doesn't require you to know how to find this integral, although if you do, you can do it that way if you wanted to. All it requires us to know is the fundamental theorem of calculus. Fundamental theorem of calculus says the derivative of an integral from a constant, a, to x of some function is just that function. All this is cosine x. That's all it is. If you are ever presented on the AP test with a problem that says take the derivative of an integral from a constant to x of some function, there's no work to be done. Just rewrite the function in terms of that variable that's up in the upper limit of your integral. The derivative of an integral from a constant to x function is just a function in terms of x. These are the easy fundamental theorem of calculus problems. They don't get any easier than those ones. They do get a little more difficult when the upper limit isn't just x, it's some other function. So if we think about this, the derivative with respect to x of an integral from 1 to x squared of cosine t. Well, we have to think about this in terms of the chain rule. If we let u equal x squared, then what we're now looking at is a derivative with respect to x of an integral from 1 to u of cosine t dt. Well, how do I take the derivative with respect to x of something that is not in terms of x, it's in terms of u? Well, the chain rule says take the derivative of it in terms of u, so that the derivative of an integral of a function is just a function in terms of the variable, cosine u, times the derivative of u with respect to x. Well, what's du dx? We look over here, du dx is 2x, and cosine u is cosine of x squared. So really, we're just applying the chain rule here. You can pretty quickly and easily just sort of, plug that x squared in here and then multiply by the derivative of x squared. So that's what we're going to do here on this second one. I've now got a derivative with respect to x of an integral from 0 to x cubed, a constant, to a function of e to the t squared. So I'm just going to say, well, I'm going to plug this x cubed in as the t, but then multiply by the derivative of x cubed. So it's going to be e to the x cubed squared times the derivative of x cubed. Right. And so the derivative of x cubed is 3x squared, and then e to the x cubed squared, well, the power to a power, multiply the exponents, is e to the x to the 6. We got 3x squared e to the x to the 6th power. In this one, we'll note that it's not a constant to x, it's actually x to a constant. And so we have to think back to those rules. We had a rule way, way, way back when we were working earlier today. Right here, that said, if I want to flip the limits of integration, just but a negative sign in front. Easy enough. Let's do that. Okay. So I want to flip those limits of integration. Now I have a derivative with respect to x of -1 times an integral from phi to x of 3t sine t dt. And, well, taking the derivative of -1 times something is just taking the derivative of a thing and then making it negative. So this just becomes negative 3x sine x. So, not too bad. For this one, we're now looking at a derivative with respect to x of a function to another function, an integral from one function to another function of 1 over 2 plus e to the t dt. So in order to do this, we kind of need to think about what's happening with that second part of the fundamental theorem of calculus. It's saying that, well, I'm going to integrate this thing inside of here. I'm going to find some function, and then that is its integral and evaluate it at x squared. Right? And then I'm going to evaluate it at 3x, and I'm going to find the difference between these. So we could say, let's let capital F of x be an antiderivative of 1 over 2 plus e to the t. So then this integral part, still have the derivative in front, but the integral part is just capital F evaluated at x squared minus capital F evaluated at 3x, using the second part of the fundamental theorem of calculus. And we could have used this method on the previous ones too, but the other ones were, I think, straightforward enough that it's not quite necessary. But then when we take the derivative, we'll now recognize that the derivative with respect to x of capital F of x squared, well, it should just be little f of x squared, but then times the derivative of x squared. Right? So we're going to have the derivative of x squared times little f of x squared, and then minus the derivative of 3x times little f of 3x. And we can put all that together pretty straightforwardly. The derivative of x squared is 2x. So we'll have 2x times 1 over 2 plus e, 1 plus 2 plus e to the x squared. And the second half of it will be the derivative of 3x, which is 3, over, and now it'll be 2 plus e to the 3x. And you'll see questions like this occasionally in the multiple choice of the AP test. So not too bad. You don't even really need to show all this work. Once you get used to how integrals work, you'll probably just go straight to putting them in your requirements and not actually write out any of this. Here's one more similar to that one. We'll try and do this one without showing quite as much work. So we know that we're going to have to plug in x to the 4th into this. And so let's start with that. E to the x to the 4th minus natural log of x to the 4th. But we have to multiply all of that by the derivative of x to the 4th. And then, based on that second part of the fundamental theorem of calculus, we're going to subtract, and then it's going to be the derivative of sine x, which is cosine x, times this thing evaluated at sine e to the sine x minus the natural log of sine. And so, while it's not a real pleasant looking answer, that's it. That's all there is to it. Evaluate the upper limit into your original function when you have a derivative of an integral. Make sure you multiply by the derivative of that upper limit, and then subtract the original function evaluated at the lower limit, and make sure you multiply by the derivative of that lower limit. And that's about as difficult as these fundamental theorem of calculus problems. we're going to take a look at one last thing here today. And it's going to help us apply some of those integral rules. So this often comes up on the multiple choice also, where they'll give you a couple of functions, f of x and g of x, where they don't tell you what the functions are, but they'll give you some known values of some integrals around them. So the integral of 1 to 2 of f of x is -4. We know that the integral from 1 to 5 of f of x is 6, and the integral from 1 to 5 of g of x is 8. And then they'll ask you to find some other integral that's related to this. So in this first one, we've got the integral from 2 to 2 of f of x. We don't actually need any of these other integrals to figure that out. We know the integral from a to a of any function is just 0. To find the integral from 1 to 2 of 3 f of x, we'll use that first rule that said we can just pull that constant out. This is 3 times the integral from 1 to 2 of f of x. And if we look up here, we know that the integral from 1 to 2 of f of x is -4. So this just becomes 3 times -4, or -12. And for the third one down here, we've got the integral from 1 to 5 of f of x minus g of x dx. Well, we had the rule that said we can just separate that into two different integrals. So this is just an integral from 1 to 5 of f minus the integral from 1 to 5 of g of x. And the integral from 1 to 5 of f, we've got that up here, it's just 6. And the integral from 1 to 5 of g is 8, and 6 minus 8 gives us -2. And we've got the same three values for the integrals here, but now we want to find the integral from 5 to 1 of g of x. Well, that's equal to the opposite of the integral from 1 to 5 of g of x. And if we look, well, we know the integral from 1 to 5 of g of x is 8. So this is just -8. And then the last one, to find the integral from 2 to 5 of f of x, we need to notice that we already have the integral from 1 to 5, and we've already got the integral from 1 to 2. And if we think back about that rule, here's 1 and here's 5. And here's f of x. Obviously, this isn't an appropriate representation of what f of x really looks like, but it doesn't really matter just for our purposes here. Here's 1 and 5, and well, we want 2 to 5. So if I want this piece, I've got to take the whole thing from 1 to 5 and just subtract off the part from 1 to 2. So this should equal the integral from 1 to 5 of f of x dx minus the integral from 1 to 2 of f of x dx. And well, the integral from 1 to 5 of f is 6. And the integral from 1 to 2 is -4. 6 minus -4 gives us 10. And that's where we're going to leave it today. So we've taken a look at the first and second part of the Fundamental Theorem of Calculus and looked at the proofs of them and applied them using some questions that are fairly common on the AP test. And that's going to be the end of our 50-some page intro to integrals. And starting next time, we're going to develop the rules for integration that are going to make life a lot easier. So we don't have to use the limits and the summations, and where we can actually find the area under pretty much any curve we want to. So that's the next time and basically the rest of this unit.